Thank you. Okay, so the next quiz is going to be on Thursday. Okay, so this is just more of a continuation of these acids and bases, titration, equivalence point, that type of thing. Okay, which we'll talk more about that on Wednesday. So right now, let's talk about the lab. All right, and which is going to form the whole basis of the assignment we're going to have today. So you had two distinct parts to the lab. The first part, you took 100 milliliters of water and you dissolved some mass of KHP in it, maybe around 0.5 grams. Okay? So you didn't keep track of the pH in the first part because it didn't matter. Okay? We weren't after the hydronium ion concentration. You were just trying to find the molarity of the sodium hydroxide that you added to it. Now, what we did is, and here's the difference between the different parts of this lab. The reason that we didn't keep track of pH is because pH didn't tell us anything. Okay, that wasn't what we were after. We could, but it wouldn't have told us anything, because what we were trying to find is the molarity of the sodium hydroxide. And at the end of the day, to find the molarity of that sodium hydroxide, you need moles of the sodium hydroxide divided by the volume of the sodium hydroxide. Now, one of the key things you've got to be able to do is determine when is it important to worry about a measurement and when is it not. Okay? So when we dissolved that KHP in the 100 milliliters of water, okay, and you had a mass of 0.5371 grams, 4 significant digits, very, very precise measurement. Why didn't I have you write down the volume of the water that you added it to? Irrelevant. It doesn't matter. Okay? All the water is doing is allowing the KHP to dissolve. Okay? So in this situation, the volume of the water is irrelevant. It doesn't matter. Okay? All it's allowing to the KHP to do is to dissolve and turn into ion. Okay? That's it. That's all it did. This is why you don't need that volume. It's not there. Is it important? Do we need the water? Yeah. Is the volume going to be part of the story? No. So what you do need is the moles of the sodium hydroxide. That you need, but you don't have the moles of the sodium hydroxide directly. But what you do have is the mass of the KHP. But you know, the KHP and the sodium hydroxide react in a 1-to-1 ratio. So here's the bigger idea that you need, right? Is that you have this KHP in the beaker. It's dissolved. You add sodium hydroxide. The KHP and the sodium hydroxide react in a 1-to-1 ratio. Okay, that's what you really need. That's the crux of it. So if you know how many grams of KHP that you have, then you know how many moles of KHP that you have, then you know how many moles of sodium hydroxide that you have, because it's in a 1-to-1 ratio. So you don't start with moles of sodium hydroxide, you start with moles of KHP. But because it's a 1-to-1 ratio, you can do the stoic and end up with the moles of the sodium hydroxide. Boom, there you go. So that's how you're going to get the top part of this equation. Hey, moles of sodium hydroxide. The volume, and this is the volume of the sodium hydroxide. It is not the volume of the water that you put in there. The water didn't react with anything. Not relevant. Okay? Not part of the story. But what I do need is the volume of the sodium hydroxide that you added. So you know the reaction was finished when that beaker took on that faint hint of magenta. Okay? Like, look at this, top shelf. Some of you were so proud. One more drop. Like you were just like, come on, one more drop. Okay? All right? You were all about it. It was cool. It's like, ooh, look at us, we're chemists. Okay. So at that point, you knew the volume of the of the sodium hydroxide. You knew the molarity. You could find the volume. And I'm guessing most of you got molarity of that KHP to be 0.9 something. Okay? That's about what everybody's the molarity of the sodium hydroxide is, something around there. And that's what I mixed it up for. Okay? I shot for something around a molarity of 0.1. you got like 0.9 whatever, okay? So you did 3 trials. Find the average, find the standard deviation, okay? I don't need to see how you calculate the average, but I do need to see at least one calculation of the standard deviation of that KHP, okay? It's your average minus a trial squared, an average minus a second trial, an average minus a third trial, all that squared, add them together, divide by 2, get the square root of all of that. I'm not going to expect you to have the standard deviation formula memorized, okay? But it is a key part of science. So on the quiz, you're not going to have to do standard deviation calculations. This is not AP stats, thank God. Okay. Oh, I couldn't teach AP stats in my life. Okay. So it's just boring. I think there's no way to make AP stats exciting. This is the real one.
Do you like examples?
Huh?
Do you like examples?
Gambling.
I'm surprised you don't like it.
Oh, it's just, I don't mind it, but it's just, there's just no way to like have cool toys and do explosions or, you know, it's just like, oh,
Yeah,
here's-
but
it's just
neither is
fun.
there in English.
Huh?
Neither is there in English.
And that's why
Okay,
English is
you
boring.
can appeal to emotion, you can do poetry, you can talk about, you know, African, AP stats, it's like, oh, here's the first quartile.
Well, like, it's
That's
cool.
exciting.
It shows you stuff.
Look, I mean, I studied a lot of math, and I can't make it exciting. Okay, so here's the second part of the lab. Second part of the lab, now you're after 2 things. You're after the molarity of the acid, and you're after the Ka of the acid. Okay, so you need to find 2 things, both of which you can only find from your graph. This is why you have to have such precise data on your graphs. So you've got a graph of pH, volume of sodium hydroxide on your x-axis. Hopefully your graph looks something like this, okay? And now you all understand why I said, hey, 1 or 2 drops can cause that pH to drop by a point of like 1, 1.5, literally. That's why you have to have such good data on that spike. So you should have 3 graphs that look like this. I want to see 3 lines, count them, 3 lines on every graph. Okay, here are the 3 lines that I want. The first one I want, and again, you just kind of have to estimate this, what we call the equivalence point. Okay, so at the equivalence point, which is the middle of that spike, okay, that equivalence point is what that allows us to do is find the molarity of the acid. So what you're going to do is MAVA equals MVVB. This is a wonderful equation, and we're going to use it a lot. But understand its limitations. Basically, and understand the complexity of what this shows. It looks simple, but here's the main idea. Is that when you neutralize something, the moles of the acid equal the moles of the base. Okay? That's the only time this works. And it only works if it's a 1-to-1 ratio between the acid and the base. Okay? So what's happening is that you're going to have acetic acid. I'm just going to write it as HA. Okay? And I'm going to write it as the molecular form because it's a weak acid. That's reacting with some hydroxide, and you're forming water in the anions. Okay? So here's the bigger truth, is that as you add base, the concentration of your acid, the molecular form, is decreasing. The molecular form of the ion is increasing. So the molecules of acid is dropping. It's being consumed. What we're making are anions. Okay? And this is going to be so vital in the lab today, or in the lesson today. You are making anions. Now, what is going to happen at this equivalence point is that the moles of the acid are going to balance out the moles of the base. Okay? At that exact equivalence point, you have no acid and you have no hydroxide. Okay? Everything is exactly used up. Everything's gone. The only thing that exists is the water and some anions. Okay? This is going to be such importance later on. So I'm just planting the seed right now. So when you completely neutralize an acid with a base, none of this is here. It's all water and the anion. Okay? Cool. Got it. Great. Now, to figure this out, you know the volume of the base. The volume of the base comes from the equivalence point. So that's how you're going to get your volume of your base. You're going to find the midpoint of that line, bring that line down, boom, label it. There's your equivalence point. Whatever that volume is, that's the first line that you need. That's what's going to go into MAVA equals MVVD. Okay? You know the molarity of the base. You found that. You know your average molarity. You have this number. Okay? So you have the molarity of the base and you have the volume of the base. Boom. You have the right side. You know the volume of the acid because you know exactly how much acid you put in there. You took that volumetric pipette and you added exactly 25 milliliters of acid into the solution. So the only thing you don't know is the molarity of the acid. That's the only thing you don't know. But this is why you're going to have 3 different values for the molarity of the acid, because you're probably going to have 3 different equivalence points based upon the graphs. Now, you shouldn't see a large deviation in the molarity of that point, okay, where that equivalent point is, okay, based upon your data and things like that. I doubt you got the exact same one every time. Usually there's some variation on that. Okay, so that's the first thing you can do. Find the molarity of the acid. So over there where it says the molarity of the unknown acid, I don't need to see all 3 calculations, but again, show me one calculation. I don't need to see how you did your standard deviation. If you want to write that out, great. It's up to you, because at this point I know you know how to do standard deviation. Now, here's the most important part of the lab, and this is what we're after today. To get the Ka, and I'm going to show you 2 different ways you can do this. I don't care how you understand this. I emphasize there's 2 different ways that you can think about this. One of them is to go, okay, my Ka equals my hydronium ion, so my anion concentration divided by my HA. So if you are president of the Ka club, like that equation speaks to me. I love that equation. Great. If you're into it, it's great. Now, here's the whole point of this. And listen to me very carefully, because it only works when you are half neutralized. Okay, and this is vitally important that you understand this. It only works when you are half neutralized. So if you have 0.1 moles of your acid and you half neutralize it, you're going to use up 0.05 of that, which means that's going to take 0.05 moles of your base, which means you're going to generate 0.05 moles of your anion. So listen to me very, very carefully, very, very carefully. When you're half neutralized, the moles of the acid that are still remaining equal the moles of the anion that you have produced. Whether it's a strong acid, weak acid, does not matter. Okay? You've consumed half the acid. You've produced that equivalent number of moles of your anion. Now, obviously, with a strong acid, this won't work in terms of the Ka calculation. Why? Yeah, there is no Ka value. Like, oh, can we use this with hydrochloric acid? You ask me that question, I'm going to have an aneurysm. Okay? Why can't you use this method with a strong acid? There is no Ka for hydrochloric acid. You know why? It's too big or it's undefined. So do not go, we can use this with strong acids. No, I will flip out. Okay? It only works with weak acid. It's a cool trick. It's an amazing trick. So I got Ka equals my hydronium ion concentration, which I don't know. Now, technically, when you have brackets, and you remember this, technically, when you have brackets, what's that measured in? Molarity. It's concentration, right? So this would be the moles of your anion divided by the total volume, whatever that is, 75 milliliters, whatever it is, the same volume. This would be the moles of your acid that remain divided by the total volume. Cool. Nice. When you do this, what's going to happen to the concentration of your anion and the concentration of your acid? Cancel out, because it's the same thing. Okay? But again, this only works when it's half neutralized. Okay? Only works when it's half neutralized. So when you're half neutralized, that means your Ka equals your hydronium ion concentration. But that isn't something we can measure. We can measure pH. Oh, cool. So if I take the negative log of both sides, if I take the negative log of my Ka and the negative log of my hydronium ion concentration, miracles, what do we call the negative log of your hydronium ion concentration? pH. Which also equals your pKa. You know why we don't have a whole bunch of pKa probes? Well, you can't have a standardized Ka value. You'd have to have a different probe for every type of weak acid based upon that type of Ka. That's just why we don't have, it's like, oh, Burkamp, where's pKa probes? We don't have them because it would be a nightmare. Because every Ka value changes based upon the strength of that acid. pH probes are simple. Hey, that's just based upon your hydronium ion concentration. But if you know what that pH is, then you know your pKa. So here's the second and third lines that you have to draw. So you go to this graph, and you're going to find half the equivalence point. So if your initial equivalent points would say 24 milliliters, whatever that is, okay, wherever that midpoint of that line is, you're going to go to half that volume. So if mine was at 24, I'm going to come over here to 12. Then I'm going to go up from that line. I'm going to see where it crosses that curve. And then I'm going to draw a line over here and figure out what that pH is at half the equivalence point. So here's the three lines that I want. The line at the equivalence point. The line at half the equivalence point, that's the second line, and the horizontal line that crosses that curve at half the equivalence point. And then you're going to know what that pH is. So let's say that pH is, I don't know, 4.55, whatever it is. I just made up a number, okay? And all of your pHs, make sure that you have 2 decimal places to the right of that pH. If it was exactly 4, you put 4.00, okay? Whatever that is, make sure that you have 2 decimal places to the right of that pH. So here's the heart and soul of what you're after. So if you know that pH is 4.55, guess what? You also know what the pKa value is. Okay? But again, that I cannot emphasize this enough. It only works at the equivalence point. Not the equivalence point, not 3/4, not 7/8, not pi. It only works at half the equivalence point. Now, to get the Ka, how are you going to undo the fact that the pKa is 4.55? Yeah, so to get the actual Ka value, you're going to take 10 to the negative 4.55. If you're, Burkamp, I like formulas. Fine, your Ka is going to equal 10 to the negative pH at half the equivalence point. If you really want to get fancy and write that out. Okay? Cool with all of that. 3 lines. 1, 2, 3. Okay? It only works at half the equivalence point. Okay. Now let's talk about the questions on the lab. This is going to be relevant to this. So on number 3, you're going to find the pH of taking 60 milliliters of 0.25. Now, I'm going to show you a couple of different ways you can do this. Okay? The main thing is you're going to use a Bryce chart. And I cannot emphasize this enough. If you do not know what the reaction is, the rice chart makes no sense. It is just going to be random numbers that don't make any sense at all. Okay? So, here's what's going to happen. You have hydrochloric acid. So there's two ways you can even do the reaction. You can write it out as HCl plus sodium hydroxide yielding water plus NaCl. Okay? If you're old school, hey, Burkamp, I want to write everything out, cool. That's your reaction. If you're into net ionics, which is what we're going to ultimately end up doing, so if you want to embrace this right from the beginning, remembering that hydrochloric acid is a strong acid, so technically that's existing as hydronium ions and chloride ions. I don't care about the chloride ions. Then the reason that I don't care about the chloride ions is because the chloride ions don't react with the water, because the chloride ions are the conjugate base off of the strong acid, which means the chloride ion is an extremely weak base. So the chloride won't react with the water because the chloride's going, I'm good. If I liked hydronium ions, I'd be a weak acid. Chloride goes, I'm good. Leave me alone, put it off. I'm there, but I'm not going to react with the water because I don't want to reform my acid because I'm cool the way I am. So technically, and I don't care about the sodium either because the sodium is a group 1 element and everything is soluble. So your net ionic is technically just H plus OH making water. So when you have a strong acid, strong base, here's your net ionic equation. H, literally, you're just making water. Your hydronium ion times plus your hydroxide makes water. And if you go, oh, Burkamp, I like writing things out. Fine, write things out. I don't care. Now, here's the most important part. Listen to me, listen to me, listen to me, listen to me, listen to me. This is a reaction where things are going to be consumed. Things are going to be consumed, okay? Which means you have to work in one of two things. Number one option that you're probably already familiar with is working with moles. So you know you have a 0.125 molar solution of sodium hydroxide, okay? You know you have 60 milliliters of 0.25 molar solution of hydrochloric acid, okay? So you know volumes and you know molarities. So remember, in terms of moles, if you take molarity, which is moles per liter, and you multiply that by liters, the liters cancel out and you get moles, okay? So on number 3, on this initial line, listen to me. This initial line is not concentration. This initial line is moles, okay, or a new concept which we're talking about is called millimoles. So, if you are old school, you know you have 60 milliliters of 0.25 molar solution of hydrochloric acid. So one option is you take that hydrochloric acid, you take the 0.250 moles per liter. That's what molarity means, your hydrochloric acid. And you multiply that by a volume in liters, which is 0.060 liters. You divide by 1,000. And the liters cancel out, and you're going to get the moles of hydrochloric acid. Okay? It's the only way you can do this. This is not concentration. This is not whatever. You can only work in moles. Now, and if you are a purist, if you are a chemical purist, like, Burkamp, I'm going to work in moles. Cool, do it. That speaks to you. Here's option number 2, but wait, there's more. For additional shipping and handling, you have another option. And this is what's called the millimole. Okay, which sounds like something out of like a dwarf version of Disneyland. Oh, it's a millimole. Okay, the millimole. Okay, so like Minnie the Mouse or something like that. It's the same idea, but you don't have to do the conversion from milliliters into liters. You just leave it as milliliters. So in this situation, it just saves you the hassle of dividing by 1,000. So what you can do is you notice where you have the 60 milliliters of 0.25 molar hydrochloric acid. So if you take the 60 milliliters and you just leave it as milliliter, that's the beauty of it. You don't have to convert it. And you multiply that by 0.250 moles. And this is why it's called a millimole, because it's milliliters times molarity. Okay? That's why it's called the millimole. This is what I do, because I don't want to go through the hassle of dividing by 1,000. Okay? If I can just leave this in milliliters, cool. It saves me that hassle. So here's the point. If I do this, if I take 60 times 0.25, I get, up here in this reaction, I get 15 millimoles of my acid. Okay? Now, if that bugs you, it's like, Berkhamp, I can't do with millimoles. I have to do with moles. Fine. You're going to get the exact same numeric value. The only difference is where the decimal place is going to be put. Okay? You're still going to get the exact same ratio. Everything's going to work out to be the same. You just have to spend a lot of time dividing by 1,000. Okay? I speak millimole. Okay? So if you want to embrace this idea of millimole, that's cool. Do it. Okay? Do it. Or you can work in moles. But what you cannot do, listen to me, what you cannot do is leave this as molarity. You can't say, oh, that's a 0.25 molar solution of my acid. That's what you cannot do, and here's the reason why. If you just put the molarity there, you're screwed. Mainly because of the fact that if I have 5 drops of this acid, or if I have 5 gallons of this acid, that's a completely different number of moles that have to react with the sodium hydroxide. Right? That's why you need to work in moles or you need to work in millimoles. Pick one. I don't care. But tell me what you're working in. Okay? Don't just write down a number up here and go, oh, Berkhamp will know what that. No, Berkhamp will not know what that is. Okay? You can either put moles, you can put millimoles. Okay? Now, if you want to continue on with millimole theme, if you do the hydroxide, you got 60 milliliters of 0.125 molar solution of hydroxide. You do that math, you get 7.5 millimoles. And I don't care about the chloride in this situation because it's not going to react with anything. So I'm going to lose 7.5 of this. I'm going to lose 7.5 of this. So right away, I know that I'm going to have excess acid left over because I'm going to consume all of my base. Okay? This is going to be important. My base is gone because I have less moles of that. I'm going to have some acid that's left over. So this is going to become 7.5 millimoles. So now, because I have excess acid, is my pH going to be bigger or smaller than 7? Smaller, because I have excess acid. If I had excess base, my pH would be above 7. Okay? So, at the end of the day, you want to find the pH. To find the pH, you need the negative log of your hydronium ion concentration. That's the only way to find your pH. So, here's the story. This is not a weak acid. This is a strong acid. So I can't sit there and go, oh, it's half neutralized. My pH equals my pKa. I can't do that. Why? The strong acid, there is no Ka value. If it was a weak acid, I could. And you'll see that in just a second. But in this situation, I can't. So this is how many millimoles I have left over, or however many moles you have, which would be like 0.0075 mole. You need molarity. So you have to have it as molarity. So now you're going to take that and you're going to divide it by the total volume. So the total volume in this case is 120 milliliters. This is where the magic happens. The milliliters cancel out. What units are you left with? Molarity. Okay? Now, if you've worked in moles, God bless you if you did. Okay, great. If you worked this in moles, fantastic. Okay? Then what units does your volume have to be in? Your liters. So you work in millimoles and divide by milliliters, or you work in moles and you divide by liters. You can't cross over the two. You're either in the magic kingdom of millimoles or you're in the standard land of moles. You cannot, there is no ticket that connects the two kingdoms. Okay? Work in one, work in the other. So your answer to number 3 would make a horrible GPA. Okay? Cool with that. Great. Now, your answer to number 4 would make an even worse GPA than your answer to number 3. Bad. On number 5, when I say write the disassociation for sodium acetate, let me make sure everybody's cool with what I want. Not make this difficult. All you have to do is write the formula for sodium acetate, NaC2H3O2, and separate that into sodium ions and acetate ions. Okay, that's all you have to do. Okay, that's it. This is soluble because L sodium is in group 1. That's all you have to do. There's your answer to number 5. Do not make number 5 complicated. That's all you have to do. All right? Now, 7 is going to lead into 8. And here's the difference. If this had been sodium chloride, and you generated sodium ions and chloride ions, this chloride ion, keep in mind this is in the presence of water. We didn't write the water, but water is a vital part of the story. Will the chloride ion react with the water to make HCl and generate a hydroxide? Absolutely not. Not going to happen. Why?
Strong acid.
Strong acid, which means it has a horribly weak conjugate base. This chloride ion sitting there with 8 goats could care less about the water, doesn't alter it. Okay? Fluoride ion is not going to react with water because it doesn't gain anything from it. Okay? It basically doesn't have the moxie to go up to the water and go, say, Holmes, give me a proton. Water goes, go away. Okay? You have your 8 goats, leave me alone. Okay? Water is, this is going to be important. If the conjugate base is from a strong acid, this is why you need to know your strong acids. If the conjugate base is from a strong acid, you put that in water, nothing happens. Okay? Because it's happy, it's stable. Okay? It has the 8 chihuahuas, it doesn't want anything else. It's cool. Okay? However, if you, and this is what's going to form the base, this is why I'm transitioning from this into the assignment today. However, you put the acetate ion in water. Now what's going to happen?
Take it from water.
Yeah, what's it going to take? It's going to take the proton. So it's going to come up to the water. I've lost my proton. Close enough? Okay? So this acetate ion is going to come up and it's going to go, hey, can you spare a proton? I'm missing one. The water goes, really didn't like it anyway, here, take one. So it gives a proton to the acetate. Now, when that happens, what do you have left over? Now you're generating hydroxide ions. You're generating a base. So now, you're going to make the reform the acid, HC2H3O2, plus your hydroxide ion. Nathan Nelson, what do the sum of the charges on both sides have to equal?
They have to be the same thing.
They have to be the same. I don't care what it is, they just have to be the same.
Berg, I missed that on my assignment.
I realize this is why I'm asking you again.
Yeah, I got locked in now.
Yeah, okay, locked in on this one, okay? So, the charge over here is -1. The charge over there, -1.
Bueno.
Bueno. One of the great conservation laws of science. Charge has to be conserved. Now, I put this in water, you just get the chloride ion in water. Oh, that's exciting. Cool. Okay? No. The acetate, though, comes along. Now, the acetate, is that going to act as a conjugate acid or a conjugate base?
Con base.
Con base. Why?